Section 12.3, the dot product. Previously, we learned how to add and subtract vectors and how to multiply vectors by scalars, but we didn't learn how to multiply two vectors together. It turns out that there's two different useful ways to do this, the dot product and the cross product. So first, let's learn about the dot product. Remember that if we have a scalar times a vector, like let's say c times a vector v, then that just takes a vector v, let's say, and it makes it bigger or smaller, or it reverses its direction. But if we have two vectors, let's say v and w, and we take their dot product, then what happens is we end up with a scalar. So we end up with just some number in the end. We don't get a vector output. So two vectors go in and no vectors come out. What we do is we take each of the components of those vectors, so we write, let's say a and b, as a1, a2, a3, and b1, b2, b3, and then we just multiply the corresponding components, so a1 and b1, a2 and b2, a3 and b3, and then we just add those together. So when we add a bunch of numbers together, we just get a number in the end, not a vector. So let's do an example of this really quick. If we've got 2, 4 dotted with 3 minus 1, then all we have to do is just take the 2 times the 3 and the 4 times the minus 1 and add those two products together. So we have 2 times 3 plus 4 times minus 1 equals 2. So the dot product is not a vector, it's just a number 2. For the next example, it's a three-dimensional vector product, so we just do minus 1 times 6 plus 7 times 2 plus 4 times minus 1/2, and then that just adds up to 6. We can also do this if we have ijk notation. We just multiply the coefficients of I. I shouldn't have drawn that arrow because notice that there's 0i over here. So that's what has to multiply. I have to take 0 times 1, because those are the coefficients of I, and then 2 times 2 for j, and then minus 3 times minus 1 for k. So let's do that. We've got 1 times 0 plus 2 times 2 plus negative 3 times negative 1. And that just equals 7. So we have a number of properties of the dot product. If we have a, b, and c as vectors, so this c is a vector, this c is a scalar. It's not such great notation, but you can see that one's italicized and one's bold. So we only use the vector c once for our distributive property, but we use the scalar c, I think, a little bit more often, but I guess not in these properties. Anywho, so we can take the dot product of two vectors, and it turns out that that is just the length of the vector, the magnitude of the vector squared. Very useful. It also turns out the dot product is commutative. The dot product is distributive over addition. It is also distributive over scalar multiplication. And if you take 0 dotted with any vector, it's 0. So these are not too difficult to prove. You can just write each of these vectors in terms of their components, a1, a2, a3, b1, b2, b3, and so on, and then just write out what you get when you take the dot product, and you'll see that it equals what you want it to equal. A really interesting theorem is that you can use the dot product to figure out the angle between two vectors. It turns out that the dot product between two vectors is equal to the product of their lengths times the cosine of the angle between them. So proving this is kind of cool because you use the law of cosines. So we draw this triangle over here, where here's vector A, here's vector B, and we're going to dot those together. Notice that if you take A minus B, that's this vector over here. You can get that by taking minus b, so that'll be b going, let's say, this way, and then you would take that and put it at the end of a, and then draw that vector, and you can see that's just this vector. You can also do it using the parallelogram law. In any case, we've got our nice picture over here. We apply the law of cosines to our triangle, which says that we can take the distance from this part to this part. It's AB, capital AB. So that distance is the length of the side of the triangle. And remember, the law of cosines says that that length, let's say c squared, is equal to a squared. Should use little letters for that. A squared plus b squared minus 2ab cosine big C. So this should really be a smaller c. It basically says it's the Pythagorean theorem, a squared plus b squared equals c squared, but you also subtract off minus 2ab cosine c because you can't do the Pythagorean theorem on a triangle that doesn't have a right angle. So you have to adjust it slightly to get the law of cosines. I reused these letters a, b, and c, but in the formula that I'm giving you, it's just to refresh you for the law of cosines. They're not the same a, b, and c in the context of the problem. In any case, the formula tells us that we take this side length, which is this one, we square it, and it equals the sum of the other two side lengths, which is just the distance from the origin to A, distance from origin to B, and then we subtract off those two distances, A and B, times the cosine of the angle between them, theta. So we end up substituting in, because the distance from A to B is just the length of the vector A minus B. The distance from the origin to the point A in the triangle is just the vector A, length of the vector A squared, then we add length of the vector B squared, etc. So it substitutes into our vectors really nicely. Then we know that the first property of the dot product says that the dot product is the same thing as the magnitude squared. So we go backwards. We replace the magnitude squared with the dot product. So we replace a minus b squared with a minus b dot a minus b. And then we FOIL out using the distributive property, because we know that from this property right over here, if we're dotting vectors under addition, then we can just distribute. So we do that in a FOIL fashion over here. And we end up with this. So then a dotted with a is just length of a squared. A dotted with b is same as b dotted with a by our commutativity property. So that's minus 2a dotted with b, and then b dotted with b is just b squared. Now notice on both sides the a squareds cancel, the b squareds cancel. So we just have minus 2a dot b equals minus 2 length of a, length of b cosine theta. And then we just cancel out the minus 2's, and we're left with exactly what we wanted to prove. So now we have a way of finding the angle between vectors. So as an example of this formula in action, how about we find the dot product, given that we know the lengths of vectors and their angle between them. So we have a dotted with b equal to the length of a, length of b, times the cosine of pi over 3. So that's 4 times 6 times 1/2, which is 12. Usually, though, we will not be looking at lengths and an angle. We wouldn't usually know what those are, and we'd have the dot product. It's usually easier to take the dot product than it is to do the other direction. So let's just change our formula a little bit. What we can do is divide both sides by the length of a times the length of b, assuming they're not 0, and we get this corollary right over here. which says that the cosine is equal to the dot product over the lengths. So we'll use that pretty often. How about we try finding the angle between these vectors? So first we need the lengths. So the length of A is just the square root of 2 squared plus 2 squared plus minus 1 squared. So that's just 3. Then the length of B is just the square root of 5 squared plus minus 3 squared plus 2 squared, and that's just the square root of 38. So now we'll take the dot product. We get 2 times 5 plus 2 times minus 3 plus minus 1 times 2, and that's equal to 2. So we'll use our formula from our corollary that the cosine of theta is equal to the dot product divided by the lengths. So that's just 2 over 3 times the square root of 38. So that means that that's what cosine is equal. So we do cosine inverse to get theta by itself. So theta must equal cosine inverse of 2 over 3 times the square root of 38. And we can use a calculator to approximate that as about 1.46. And that's in radians. If you wanted in degrees, you could say that that's equal to 84 degrees. Two non-zero vectors A and B are called perpendicular or orthogonal if the angle between them is pi over 2. So we will often use the term orthogonal for higher dimensional perpendicular because we only really refer to perpendicular in 2 dimensions, but in, let's say, 3 or more dimensions, we might still want to think about what it means for vectors to be perpendicular to each other, so we use this fancy term orthogonal. The zero vector, by definition, is just considered to be perpendicular to all other vectors. Then we have a theorem that 2 vectors are orthogonal if and only if the dot product is 0. So that's pretty useful because this means that now we have a way to check if vectors are perpendicular, and we also have a way to check if the dot product is 0. So if theta is equal to pi over 2, so first we'll assume that the vectors are orthogonal. Then we have the dot product equal to the lengths times the cosine of pi over 2 by our formula. But that's 0. So that means that if the vectors are orthogonal, the dot product will have to be 0. Let's prove the other direction now. If you assume the dot product is 0, then using our formula, we get that the cosine of theta has to be 0. So that means theta must be pi over 2. So either way, you get the vectors are orthogonal when the dot product is 0. So let's do an example. We will show that these vectors are perpendicular. So we'll take 2i plus 2j minus k. We will dot that. I forgot my dot. With 5i minus 4j plus 2k. And that just equals 2 times 5 plus 2 times minus 4 plus minus 1 times 2, which is just 0. So that means they must be perpendicular. The direction angles of a non-zero vector, A, are the angles A, B, alpha, beta, and gamma in the interval from 0 to pi that A makes with the positive x, y, and z axes. So here's some vector floating in space, A. Then the angle between A and the x-axis is alpha. Angle between A and the y-axis is beta. And the angle between A, and the z-axis is gamma. So then you could take the cosines of each of these angles, and they're called the direction cosines of the vector. Okay, so the direction cosines of a vector are actually the components of the unit vector in the direction of A, which is kind of cool. So if we take a vector, we divide it by its length, we get the cosine of each of the angles between the vector and the each of the axes. It should kind of make sense because all of those are defined on the unit circle, the cosines. So let's prove this really quick. We have, by our corollary, the cosine of the angle between vectors. So let's say we do for alpha, then that's the vector A and the vector I, because we're using ijk notation. I is along the x-axis. So we take A dotted with I, we divide it by the length of A times the length of I, and that must be the cosine of alpha. Well, A dotted with I just gives you A1 because I is 1, 0, 0. So you get A1 times 1 plus 0, which is just A1. And then the length of I is 1, so it's just length of A times 1. And then similarly, we get A2 over length of A is the cosine of beta, A3 over length of A is the cosine of gamma, and therefore we can write the vector A as A1, A2, A3, and replace those with, let's say we take this length and multiply it over here to get A1 by itself, so replace that with length of A times cosine alpha, and the same thing for the other two components. But then this length of alpha is a scalar, so we can pull that out. So we factor out the scalar, and we get the length of A times the cosine is equal to A. We divide both sides by the length, and we get the unit vector version of A is equal to the components with a cosine of each of the direction angles. So let's do an example real quick. We'll find the direction angles of the vector 1, 2, 3. So first we need the length. So let's get that out of the way. The length of A is equal to the square root of 1 squared plus 2 squared plus 3 squared, and that's just the square root of 14. So now we have the cosine of alpha must be equal to 1 over the square root of 14. The cosine of beta must be equal to 2 over the square root of 14. And the cosine of gamma must be equal to 3 over the square root of 14. Because it's just equal to the unitized version of this. You take the vector A, you divide it by its length. That must be equal to these direction angles with the cosines. Okay, so now let's solve for the direction angles by taking cosine inverse. So we get alpha must be cosine inverse of 1 over square root of 14, which is about 74 degrees. Then beta must be cosine inverse of 2 over square root of 14. So that's about 58 degrees. And lastly, we have gamma equal to cosine inverse of 3 over square root of 14. So that's just about 37 degrees. The next interesting thing we can do with vectors in our dot products is projections. So if we want to take vector A and we look at a vector B, I want to project B down so that it lands on top of A. Basically its shadow lands on top of A. We call that the projection of B onto A. So in our picture, we're just taking the orange vector and we are taking the shadow of it on the purple vector, so that's just this green vector right over here. So you could see that from our picture it's not necessarily the same length as B, and it's not going to be the same length as A either, but it is in the same direction as A. So if we want just the length of this projection, which is a vector, then that length is called the component of B along A. So remember that that's the length of B times the cosine of theta by what we just did in our previous definition. So the scalar projection of B onto A is the dot product over the length of A. And the projection of B onto A is the dot product over the length of A times the unit vector version of A. So let's prove that really quick. If we have the dot product, well, we know that that's equal to length of A times length of B times cosine theta by what we did before. And if we divide both sides by the length of A, then we get length of B times cosine theta, which is just the scalar projection. So that's how long the projection is. So we could then multiply by the unit vector to give us the vector projection. Because if we take a length and we multiply it by a unit vector, all it does is make the vector have length equal to whatever length we multiplied by it. So imagine that we have this like unit vector in the same direction as A. So we take A, we shrink it down or make it bigger depending on how big A is until it's a unit vector, and then we scale that unit vector until it ends up being however long we want it to be, matching with the length of the scalar projection, the component. So once we know what the length of the vector projection is, it's very easy to get to the vector projection just by multiplying by the unit vector. So we just multiply by this guy, and then you can see that this just becomes a square, so that's how we get this. So let's do an example really quick. We'll find the scalar projection and vector projection of B onto A. So first we need the length. So let's see how long A is. Well, that's just minus 2 squared plus 3 squared plus 1 squared. So that's the square root of 14. Then we can get the length of the scalar projection, which is the component of B along A, and that's just the dot product over the length of A. So the dot product is minus 2 times 1 plus 3 times 1 plus 1 times 2, and we divide that by the length we calculated was square root of 14. So that's just 3 over square root of 14. So now we know how long the vector projection is. So we just have to take the unit vector of A and multiply it by how long it's supposed to be. So we get 3 over the square root of 14, as we calculated, is how long it's supposed to be. We want to multiply that by the unit version of A, so that's A over its length, which is just 3 over 14 without the square root, because we already know the length of A is square root of 14, so the square roots cancel, times the vector A. So that's minus 3/7, 9/14, and 3/14 as the components of the vector projection of B along A. Suppose that the constant force in moving an object from P to Q is a vector F equals PR, as in our figure. So then the displacement vector is D equals PQ. That's this guy. And the work done by this force is defined to be the product of the component of the force along D and the distance moved. So what we do is we take the component of the force along D, so that's just the scalar projection, you could think of it as, and that's just length of F times cosine theta, and then we define that times the length of D to be the work done. Okay, so then it's a theorem that the work done by a constant force is the dot product, and that's pretty instant because we know that this value over here is this value over here. Just move d to the front. And we already proved that this is equal to the dot product. Length of A times length of B times cosine theta. That was our corollary. Okay, let's do an example. Let's say we have a wagon and it's pulled a distance of 100 meters along a horizontal path by a constant force of 70 newtons. The handle of the wagon is held at an angle of 35 degrees above the horizontal path. So let's see if we can find the work done. Well, first I'll draw a very, very bad looking wagon. So you should probably look away. Something like this. And it's got to be on the ground somewhere, so I'll draw some ground. Told you it would be really, really bad. And it needs a handle. So here's the handle. The handle is at an angle of 35 degrees. So I'll put a 35 over here. Okay, we need the work. So by our theorem, that's force dotted with distance. So that's the length of the force vector times the length, or the magnitude of the distance vector times the cosine of 35 degrees. So that's just 70 times 100, because they gave those to us, times the cosine of 35. Okay, and that's just approximately 5734. And since we were multiplying newtons and meters, those are Newton meters, which is the same thing as joules. So we could say it's 5734 joules. Okay, how about a force given by a vector 3i plus 4j plus 5k, and that moves a particle from one point to another point? Well, in this case, we have a force vector, but we do not have the displacement vector. So we have displacement points. We need to make a vector out of those. Remember, to get a vector out of points, we subtract. So we can get the displacement vector equal to the vector from P to Q. So by subtracting 4 minus 2, 6 minus 1, 2 minus 0, we get the vector 2, 5, 2. So now that we have our two vectors, we can take work. We can write it out as the dot product. Before, we didn't end up actually using the dot product. We used our formula for the dot product. But now, since we know what the vectors are, we could just dot them. So we'll take 3, 4, 5, and we will dot that with 2, 5, 2, and that just equals 6 plus 20 plus 10, which is 36. And then if the length happened to be in meters and the magnitude of force happened to be in newtons, our work would be in Newton meters, which is just joules.